It's my pleasure to present our work, Bijective Mapping Network for Shadow Remove. Then, I would like to introduce the motivation of our paper. First, the shadow remove and the shadow generation procedure are interrelated. Introduce the reverse mapping process could provide a regular constraint to prove the performance of forward mapping. In this paper, we employ such manner to push the estimated result close to the reference. Finally, we laterally implement such bijective mapping learning process based on the invertible neural networks. Second, we noticed that shadows often bring obvious color degradation to images, and shadows have different effects on different RGB spectrums. For a single image, we could obtain the different shadow effect appearance under different colors with equation 1 and 2. For the whole dataset, we use equation 3 to calculate the average shadow effect of each image. And the statistic results are shown in the figure B. This conclusion motivates us to employ the color cues to guide the network to remove shadows. As shown in the above figure, our proposed framework implies a two-way mapping procedure with the help of the condition inputs in the same parameter shared framework. The green arrow means the shadow remove process, and the red arrows indicates the shadow generation process. The whole framework mainly consists of several invertible blocks. Deep into the invertible block, the detailed operation of the forward mapping could be expressed as equation 4, and the operation of reverse mapping could be expressed as equation 5. Then, I would like to introduce the estimation of the shadow environment color and the shadow environment color guidance model. First, we adopt the subnetwork to estimate the shadow environment color with corresponding loss function, and the color maps are defined as equation 6. Shadow environment color guidance models are affine transformation functions in the invertible block. This model is built on the pyramid multi-scale structure. At each scale, color map and the mask are used as condition inputs, and the detailed operation at each scale can be expressed as equation 7. Here, we show the experiment results. This is the shadow removal quantitative evolution on the two real-world datasets. Obviously, we surpass the state-of-art method on the PSR metric. We also achieve the best performance in terms of RMSE metric. On the AICD dataset, we verify that, use the detected mask, our method showing the slight decrease in deshadowing performance, and our method could robustly remove these shadows with inaccurate mask as condition inputs, as shown in the above figure. Then, we conduct the aberrant study to verify the effectiveness of models of our method. Obviously, when we remove the backward loss of reverse mapping, we found that the deshadowing performance have dropped a lot, both the PSNR and MSE metrics. Moreover, when we remove the shadow environment color guidance, there is an obvious color inconsistency between the shadow and the surrounding non-shadow ranges. Then, we show some estimated results among our method and other state-of-art methods. Compared to previous method, our method could better restore the contents and the color of shadow ranges with less boundary trends. In summary, our contributions are as follows. Thanks for your listening.